Every morning, millions of people grab a solid block of soap and rub it directly onto their skin without a second thought. But if you trace that comforting little white bar back to its origins, it looks completely alien. Inside an industrial manufacturing plant, there are no solid bars. Instead, raw liquids are boiled, are mechanically crushed under massive physical forces. The smooth surface you trust on your face begins as a volatile, churning soup of complex chemicals and intense reactions. This creates a unique challenge. How do engineers take a chaotic, violent chemical reaction and force it to become a reliable everyday object? The formula begins with a heavy dose of oils, usually thick, plant-based fats. To turn fat into something that cleans, it must be combined with a highly hazardous additive. This diagram compares our starting ingredients. On the left is the stable structure of a plant oil. On the right is alkali, a highly volatile, strongly corrosive chemical compound. In its raw form, alkali is extremely caustic. If just a single drop of it touches your arm, it immediately begins to burn and destroy living tissue. The exact substance capable of eating through human skin is the non-negotiable ingredient required to safely wash it. To make that toxic formula safe for humans, chemical engineers rely on a first step called saponification. This isn't a gentle mixing process. The raw ingredients are pumped into massive, thick-walled steel tanks, where they are trapped under intense heat and extreme pressure. Under high heat, the oil and alkali molecules are agitated and forced into constant collisions. The original bonds snap apart and rapidly reorganize into tightly locked geometric patterns. The volatile alkali is neutralized, leaving a safe blend of soap and glycerin. But neutralizing the danger is only half the battle. When you look at this new substance, it looks like a thick, lumpy, unappealing paste. The chemical threat is gone, but the physical result is still unusable for the consumer. This raw soap paste is flawed. It's rough, completely uneven, and packed with internal air pockets that compromise its structure. Fixing this requires stepping away from chemistry and relying on industrial refining, a process governed by heavy mechanical pressure. Massive steel rollers grab the material, tightly squeezing the ribbon of paste to physically crush every trapped bubble of air out of the mixture. The paste is fed through these rollers over and over. With every pass, the texture shifts, turning from a chunky clump into a dense, smooth medium. It takes mechanical brute force to take chemically safe but chaotic matter and pound it into a solid, workable material. Even though the soap is finally smooth, it still lacks functional form. To give it a recognizable shape, the factory uses a high-precision extrusion machine. The refined material is pushed through a narrow opening, forcing it out as a massive, solid, endless log of pure soap. The mechanical tolerances here are incredibly tight. If the machine pushes even a fraction too fast, the continuous log snaps. If it pushes too slow, the shape deforms under its own weight. Once the speed is dialed in, an automated blade executes rapid-fire slices to chop the endless log into perfectly identical rectangular blocks. Instantly, a high-pressure mold slams down onto each block. In milliseconds, it bevels the edges, smooths the surface, and punches a logo into the center. Through strict mechanical choreography, a flowing ribbon of material is separated into exact, precise consumer units. But there is one final hidden flaw. Despite looking finished, these fresh bars are still physically soft and fragile. To solve this, the factory routes the soap into long, controlled cooling tunnels to rapidly harden the product. During stabilization, as the internal temperature drops, the moisture levels lock into place, causing a sharp spike in the soap's structural density. This final engineering step determines how long your soap will last. Without it, the bar would dissolve the moment it hit your shower water. Now that the single bar is structurally perfect, the factory shifts its focus to speed and scale. The finished units enter a purely automated packaging line. In seconds, machines wrap, seal, and box hundreds of items per minute without a single human hand ever touching the product. This blistering, continuous motion marks the transition from chemical experiment to global commodity. The chaotic formula is now stabilized, synchronized, and ready for use at a massive scale. So tomorrow morning, when you pick up that simple bar of soap in your bathroom, remember the history embedded inside it. It only exists because it survived a gauntlet of violent chemistry, extreme heat, and immense mechanical pressure. These everyday objects are the result of immense industrial discipline. They represent a system that forces volatile, dangerous elements to become the trusted tools we use every single day.